Okay, hello everyone. My name is Justin Green. I work for Premier Corex. Thanks for watching this. Premier Corex, we're a laboratory and data generation company headquartered out of Houston in the USA. I come from our Aberdeen lab. Many of you may have heard of us before as Corex. We're now part of the Premier Oilfield Group. One of our areas we do a lot of work is information damage, and that's why the European Well Productivity Forum is of particular interest to us. We're going to be exhibiting there, and I'm looking forward to my first trip out of the country this year to be attending in person. So what I'm going to do today is just show you a quick case study on some visualization and quantification we've been doing, because I know that these kind of events are always really interesting technically, and lab studies and case studies are always of interest. So I want to pick a little area just to show you some stuff we've been doing in the last year. This is actually a study from the Middle East, and it's for an upcoming paper for EWPF. So it's not specifically North Sea, but this is really fresh stuff we're showing here, and we'll be doing this, I'm sure, in Europe before long. This was for ADNOC out of the United Arab Emirates, out of Abu Dhabi. This is for their onshore wells. They picked 5 fields that they were having particular problems with low permeability reservoirs, where everything looked to be going well in the higher permeability. The drilling was good, the production was good, but the low perm zones were looking to be less good. So they wanted to identify specifically any damaging mechanisms that they were seeing that were related to the low perm, use that to help reformulate drilling fluids, or maybe even choose treatment fluids. And the paper that's coming out has 55 core floods in it. So it's a big undertaking, quite a lot of data in there. All I'm going to do today is show you how some of the interpretation was improved in this big study by visualization and quantifications. So that's what I'd like to show today, some pictures. I'll give you a little bit of a background on the project. And if you're really interested, as I said, in a couple of months, there'll be a paper at EWPF on that. The scope that we looked at here was lower permeability carbonates. So we're talking millidarcies. There was a couple of samples above 10 millidarcies. Mostly were below 5 millidarcies. The good permeability reservoir wasn't really a concern. And this was all matrix flows, so we weren't looking at fractured reservoirs here. And we looked at 3 different sets of fluids. We looked at their mud that they were currently using in the field, their current formulation as it was, to see if it was good or not, or to see if it was causing damage or not. Then once we discovered what the issues were, those muds were reformulated with that in mind, alongside some alternative mud from vendors. And then we also tried them with treatment fluids. So I'm just going to show you a couple of bits of data from them. And then the kind of data we measured were permeability, we measured fluid loss from the drilling fluids, we measured production rates, permeabilities again, and we did some visualizations and, importantly here, quantifications with nano CT scanning and cryogenic SEM. So I think the quantification is what I'm going to focus on with the visualizations, and that was used nano CT, which is kind of up the game in what we're able to do in the area. And what we also utilized was part of a patented technique which we've developed over recent years as well. So I'm not going to dive into this too deep. This is a kind of summary, this in the next slide, of a couple of SPE papers we've written on visualization of formation damage test results. All I want to really talk about here briefly is, at these kind of events like the EWPF, we hear presentations on what relationship lab data has to the field. How can we understand what lab data means for the field? And we hear time and time again, it can be confusing because there are compromises in the lab. There's a disconnect between lab and field sometimes, and context is important. If we pick perm measurements, for example, if we measure permeability the same way in a series of tests, under the same conditions, we prepare the samples the same, they're fantastic for benchmarking. If we only change one thing in each step of the way, we can compare directly what's happened in the change. However, those perms can be misleading. In a short core sample, there may be clay fines being removed, for example, increasing the permeability. And then at the same time, drilling fluid or completion fluid may go inside the reservoir and not shift out in that particular reservoir, be retained within the sample. Overall, that could equal 0 change in permeability. But when we look inside the reservoir, there's things that could cause damage and could add up to damage in the reservoir. So context is important. Things like fluid loss, production rates, even what the samples look like, add context to test data. But really understanding what's happening inside the near wellbore, what has changed, is something that we think is key to interpretation, and the technology is allowing us to do better and better things with that now. And so what I'm going to show you are some images now based upon the theory of what we call 3D alteration modeling. I've put the SPE paper numbers up there. We published that to talk about this initial technique, which broadly speaking involves scanning core samples, the entire core sample that's going to be used in the core flood at high resolution, overlaying the data on top. So if we have the middle image here is the before case at reservoir saturation. We've then done a core flood study on this one. You can see there's a mud cake sitting on the outside, but we can't see inside. What we do with this 3D alteration modeling technique is lay the two data sets on top of each other and then computationally and algorithmically line them up and compare every point before and after to look for the differences. This is basically looking for where the change and the damage is in the reservoir. And you can see in this example here, we can see we have an external mud cake, some internal depth of invasion and retention, if you want to call it an internal filter cake, and then some damage scattered throughout the sample. So it allows us very easily to see where the damage is and what its abundance is. Now, what I'm going to show you just for the remaining few minutes is where the advances have allowed us to get even better resolution and better understanding. This is the kind of imagery we can get now. This is a nano CT scan, which is a higher capability scanner, which allows us to sub-scan very small areas. You can see that's 10 millimeters. So areas of a few millimeters cubed at such high resolution, you can capture the permeability and the porosity and do things like flow velocities and flow channels through those zones of the reservoir. It allows you to measure porosity and permeability. So with those increases in ability of the equipment, we have the increase in the resolution and the potential to use this basic technique, which we've detailed in the papers, combine it with a patented technique we have for quantification of damage, and start to understand why there was differences in this study that we did for ADNOC. The good news is I'm going to show you just 4 separate samples now, and it was very simple to understand this study because it was carbonates, it involved acids. So the understanding of why the damage was there and was removed is quite simple, and hopefully the images show how that could be applied for more complex scenarios. So again, don't intend to dive right into the paper. I've taken 6 samples here, which represent the average kind of result we saw in the study. Obviously with 55, we saw a big range, but this very briefly with the original mud that they had. So what we have here is a graph of permeability as a percentage of the initial. So after we drilled the well, produced, measured permeability, if it was 100%, it would be the initial permeability. But what you can see after this red block, which is after production with the initial mud, we were looking at really high damage, more than 80% reduction in perms. When we took off the external mud cake and centrifuged it to spin it down, we were right back up to 75 odd percent. So there was a high level of damage. A lot of that was coming from the very near wellbore because we removed the mud cake and centrifuged the fluid out, and it caused a huge increase. So what we were looking for was the context of that, which I'll show you. When we determined what those mechanisms were, the mud was reformulated. You can see in this particular case, big increase in permeability, but still damage seen there. Then we tested a series of treatment fluids and alternate drilling fluids. So you can see in this that we tested 3 alternate muds and this mud that was reformulated. What happened with the 100% ones? They're essentially infinite increases in permeability. We couldn't measure the perm. I'll show you why. So with 2 of the treatments, we saw very high increases in perm. 2 of them, we saw moderate to mild increases in permeability. So the question was for the operator to help choose which one was best for the field. What happened with the damage? Why did one treatment work and another treatment not work? And what are our options going forward? So now just for the remainder, I'm just going to show you some pictures and show you the context we got from that, because again, you can take some guesses with the perm data there, and we always can take guesses, but if we have something to help back that up, it always helps it. And anyone who's seen these kind of test results will see when we see the CT scans on core samples, we do see them to a certain level of resolution, but we almost couldn't believe it when we started doing these higher resolutions, because we can see here's a scan of the near wellbore region of core sample 14, which had a drop in perm of about 65% after production. And we can see that was now quite obvious immediately that there's a mud cake sitting outside there, and I can see going inside. But because we could sample subsample regions at very high resolution, we can now even start to see individual zones where there was infiltration or retention of the drilling mud. the side effect of having such good resolution is if you could measure the porosity and the permeability and the pore space of that specific zone of the reservoir before we do the core flood and after, we can actually start to quantify where the changes were and what the damage was. So in this one, where we had quite a big drop in perm, 65%, you can see in this zone of the neo wellbore that we subsampled, before we did the study, we had about 12% connected porosity and another couple of percent of unconnected porosity that wouldn't have been effective in the core flood. After the core flood, we essentially had the same amount of unconnected porosity, but we'd lost almost all the connected porosity in this area of the neo wellbore. And you can see it goes very neatly. The shape of the mud here ties in with the shape of where we'd lost the porosity. So we can actually see the mud invasion has gone in, filled up the connected porosity in this zone of the neo wellbore, and that's why we're seeing 65% reduction in perm. So not a complete reduction in perm, because not the entire wellbore was blocked off. We obviously chose a high blockage area here. And when we looked at with the electron microscope technique, we can see these yellow areas are areas of drilling mud constituents. And this is the wellbore, the end face of the core sample, but there were still pores open, so there was still flow. That's why we had this 35% of the permeability remaining. But that straight away gave us an insight. Look, we had a quite thick drilling mud cake left over. We had infiltration a few millimeters into the wellbore. We measured 1 to 10 millimeters, mostly 1 to 5 millimeters. So really it was about the, unsurprisingly to anybody, which is why it's a nice simple study, a mud that really worked nicely for the higher permeabilities. They'd taken some compromises with the lower permeability reservoirs, and it was not suitable for the lower permeability reservoirs. So with this data, ADNOC went and looked at the mud formulation, reformulated the mud, looked at the pore sizes, looked at the bridging and particles in the drilling mud to make it more suitable for the lower permeability zones, then repeated the study with the reformulated mud. And then straight away, we could see the positive impact that the reformulation had. We can see a thinner mud cake. So there's still some mud left. It's a lot thinner. We can see the depth of invasion has gone down a bit. I am saying a bit less on average, because we did a lot of core floods and it's up and down. But when you see the data in the paper, it's a bit less on average, the invasion with the reformulated mud, which is good. And we could also see when we measured, and the quantification is what we think is important for the context, showed a really nice positive result. You can see this was 21% of the connected porosity before we did the core flood, and it still dropped, but we still had a good amount of connected porosity. So there was room for improvement. It worked positively. There was room for improvement. When we looked into the near wellbore area again, we did see that the mud was more easy to clean up. You know, the nature of the mud cake was improved with the reformulated mud, but there was still large areas of the wellbore blocked by the mud constituents. So there was room for improvement with the treatment fluid. So the final phase of test looked at a treatment fluid, and I showed you those perm graphs where 2 of them had an infinite increase and 2 of them had a moderate increase. And we're looking at carbonates here. And so the 2 with the infinite increase, unsurprisingly, are the acid-based ones, and the non-acidic ones, which one of them was simply a displacement with a low solids mud. The other one was a enzyme, acid-generating enzyme, gave less positive results. So one of the ones that was less positive, although still not terrible, was this one, sample number 39. So you can see the progression is improved. You know, it's going the right way for ADNOC here. There's no mud cake left at the end point of the study, so the visualization is quite clear on that. When we looked inside these zoomed in zones, we did still see some constituents had gone inside it. Again, we're seeing a positive improvement. We went from 20% only down to 16% this time. So that's why there was a moderate improvement, because we weren't quite at 100% of the initial porosity. We still had some mud constituents left in. So the treatment had somewhat aided. It helped with cleaning out everything on the outside, no problem. But inside the reservoir, there was still some stuff stuck in there that wasn't being shifted. So there was a zone of damage in the neo wellbore. Why did the acids give an infinite increase in permeability? I think we can all expect we're talking about carbonates here. So what we saw quite simply was etching away of that wellbore there and wormholing. You can see a really thick wormhole here. When we looked at it at a higher resolution, we can see these delicate, quite high surface area wormholes, and then the main hole that had burnt through the reservoir there. So the infinite permeability rise was because we'd increased this huge conduits through the reservoir. Then what we also did was we went and looked and zoomed in on that end face where there was some exposed end face left. And we did see that there was mud constituents left. So there was still that zone very near wellbore of damage, of retention of mud. But as soon as the acid gets past that couple of millimeters of damage, which you can see it did quite readily, it basically bypassed and made it less relevant. So in this carbonate reservoir, as long as the wellbore integrity was maintained, then acidizing that near wellbore as a side effect, this was designed to remove the mud, but it actually acted as a near wellbore stimulation as well. And so, as I said, very simple set of results to explain and put in context, but the visualizations did help us understand exactly why the behavior was as it was and allow us to quantify. Obviously, for the acidic one, I haven't quantified it because it would all be infinite increases, and that's not a very good to show in a bar graph of changes in porosity, but that allowed us to basically put the story together. And as I said, a simple story here, and where more complex stories are involved, it will add a nice bit of context as well. So just some final thoughts. We believe that these kind of visualizations are increasingly going to add context to core flood studies. As the technologies have come to us, these are going to have a more powerful tool, and watch out for more of these events like the EWPF, and we'll certainly be showing these on our stand when we're there. And ADNOC said that these results helped them very much with the redesign of the drilling fluids and helped us understand which ones to use. And it helped actually understand, we went and did one test with their initial ongoing mud with the acid, and it really helped. So actually they understood from why it was acting as an improvement. They could go into existing wells and use the acid as a kind of post-production stimulation treatment as well. So if you're interested, watch out for this ADIPECT, and I'll be running some webinars on it after. Thanks for paying attention, and thanks for your time, everyone. And I think we have some of our committee on who might be wanting to have some comments or questions.
Oh, Justin, that was an excellent presentation. Thank you very much. I look forward to actually chatting with you about it next month. Thanks. In the European Well Productivity Forum that we're having in Stavanger. So myself and Dave, I've been working on the technical committee since the first one in planning since 2019, and Tony's joining us here as one of our sponsors from 360 Energy. We'd like to ask you some questions if we may.
Please.
Don't worry, we won't make them too difficult. So can you expand on this application that you've done for ADNOC for more North Sea type wells in more unconsolidated sort of reservoirs? Because that was a very consolidated rock that you were working with there.
Absolutely. I think that this is the European Well Productivity Forum. So I guess people are going to be thinking, what context or what relevance does it have to me? And I think the thing to say is that we were kind of lucky that we did some of these develops on a really low parm carbonate reservoir, because that's more tricky to do it on with the slightly higher density of the reservoir, with the smaller pores, with the smaller conduits through the reservoir. It makes it a bit more challenging to actually capture this stuff in good resolution. When we think of many of the reservoirs, especially unconsolidated reservoirs, we're going to have higher parm, we're going to have bigger pores, we're going to have bigger conduits, so we can capture even better resolution on that data. So when we've done this technique so far on sandstones, we've got some really fantastic resolution on that. I think that the quantification is going to be really good on that as well. Unconsolidated, I think it's very good because it's also going to allow us to see, as the resolution is allowing us to capture individual grains, it'll be very easy to see how the reservoir is changing with production as well. Things like changing the shape of pores. We can actually, in a sandstone, an unconsolidated or poorly consolidated sandstone, you could essentially create a pore mold with one of these techniques and show the pore space before and after, and see how the shape and size and distribution has changed and quantify that, which I think is going to be very useful. One of the other applications we think this is going to be useful is not just in rocks. I think that things like in sand control, for example, looking at sand packs in gravel packed reservoirs and how the sand packs block up or filter out the sand. This is actually applicable to that as well, and seeing how that changes with time or before and after a study.
Yeah, thank you very much.
Again, I'd like to thank you for a very interesting presentation. My question is, there's two questions I have actually. You mentioned it was an RDF design that was made for high permeability. Could you allude a little bit on what that fluid was and what the alternative muds and the treatments? Obviously, one was very clearly a acid treatment, 15% HCl, but what was the other treatment? If you could describe that for us.
Yeah, so we started off with the field. So it was essentially an in-house ADNOC designed drilling fluid. So it wasn't a vendor drilling fluid. They designed it, and that was the base case, and it's what they drilled previous wells with. They didn't tell us every single ingredient that was in that. They gave us their field mud. We don't mind testing mystery muds. And then they used that data from the first phase to do the reformulation, as I said, but they also took that opportunity to go through some of their vendors and get some alternate fluids. And so what they did was they got 3 different vendors to supply them an alternate drilling fluids. And that's what 1, 2, and 3 are. Obviously in the paper, we can't refer to what the vendors are. But in hand with that, the vendors also gave a treatment fluid that went with that. So we tested the raw mud, or the muds alone, if you like, with no treatment. We tested their mud they were using, the hopefully better version of the mud they were using, and their vendor alternative drilling fluids. And then there were some paired treatment fluids. So with the ADNOC internal mud, they just went for a straight hydrochloric acid flush. With the vendor ones, we had one that was an acid flush. We had one that was an acid generating enzyme. And we had another acid generator one. And then there was one, interestingly, which was just a sieved or solids free drilling fluid, so there wasn't actually any active ingredients in the treatment, because I think their angle that they'd come from was seeing the previous data was a lot of it was on that mud cake cleanup, external mud cake cleanup. So they were hoping by removing that, it would help remove the internal, or make the internal stuff more easy to shift. And you know, the thinking wasn't terrible, because when you looked at the 2 non-acid ones, they didn't perform massively differently with the active and non-active in them. In this case, it was a carbonate reservoir. There was carbonate in the drilling mud. No surprise that the acid gave a slightly higher stimulation result. But again, this is just a formation damage study. There's a field-wide context in this. There may be, as I said, wellbore integrity. They may not want to significantly acidize the neo wellbore. So that's why they had some of the information from these other treatments to say, okay, we can get a moderate improvement if we use these less aggressive treatments. And if we're willing to look at acidizing the neo wellbore, then as well, then we can use these. So that was the treatments. And like I said, we dive into that in the paper as well.
Thank you.
Hi, Justin. I guess just like to add my thanks from the rest of the team as well for a really excellent presentation. I think, you know, certainly seeing the level of resolution that you're getting now in nano CT is really quite exceptional. You know, it's certainly not seen anything to that level before. But I guess my question around this is, you know, this is really interesting information, but you know, what value is this quantification, this type of test bringing to our understanding of formation damage? And you know, is this something, obviously you want to take it further? Where do you see this going in future? Where can we see this technology going in future with respect to formation damage?
Yeah, thanks. And that's really good point, because we always think about how can I use the data? If I'm spending money on it, can I use it for multiple uses, and can I use it in a more quantifying way, which is what we're thinking about here with the 3D alteration modeling we've been doing for a number of years now. That's been qualitative, and you know, it gives good context, but it doesn't tell us numbers. And this is a kind of another step along the way to being fully quantitative. And obviously the logical next step for this is, how can I use this data to improve my models, for example, or can I upscale this to a wellbore? That's obviously the next step. You know, the kinds of people that are on the call here will be thinking, what can we do in terms of upscaling this and saying, can we take some core flow data and bridging this out to areas we don't have core, or to wells that we don't have core we've drilled? Can we upscale that? And so that's what we're thinking. Obviously, that is a huge step, is modeling. There's still a gap between field and lab models for a good reason. There's a gap there which is difficult to bridge, but we've got to try and bridge that as an industry. So upscaling is going to be one thing. Another thing is going to be, you saw we were cutting out small chunks of the rock because of computational power and actually storage. You know, in memory storage of computers, to actually scan an entire core sample at the kind of resolution, we're getting good data here. When we first looked into it a few years ago, to do a scan before and a scan after at sub-micron resolution of an entire core plug sample, is that there wasn't enough hard drive space in the world to do that at that point. So you're using a lot of data and a lot of processing. So as computational power increases, we may get this kind of resolution for an entire core sample. So that's going to be a next step as well. But I think the obvious big step is, can we scale this from a core sample to a bed, to a well, to a field, is a key question. I think that's going to involve a lot of disciplines, not just the lab guys, and it's going to need to modeling guys, engineers. But the good news is, you know, the data that anyone who's seen computational fluid dynamics, for example, will recognize the kind of flow paths I was showing in those images. So already that data can be output into models, either numerically or to be popped into CFD models. So already there's an opportunity, but I think as an industry, you know, we'll be talking about this at the European Well Productivity Forum. I'm sure will be field context, lab context, and how can we do things better? I think that's what we're trying to strive towards. Is there's a bit of a gap there between lab and field, and is there a way to bridge it? And this, we believe, is going to be one of the ways.
Yeah, no, excellent. Thanks very much, Justin.
Thanks.
Well, Justin, I suppose from everybody here, say many thanks for this presentation today, and I suspect you have lots of questions being asked of you next month when we see you in person. Thank you
Thanks very much, Kirsty, and thanks everyone who's watched to this point. Thank you for your attention, and if you're coming to EWPF, come and say hello. I'll be at our stand.